The James Webb Space Telescope discovered something in its very first deep-field image that no scientist had prepared a press release for. Pointed at a patch of sky so small you could cover it with a grain of sand held at arm's length, the telescope returned a picture crowded with galaxies. Not faint smudges, not the wispy proto-structures theory predicted, but fully formed, brilliantly lit cities of stars. Mature, massive, and completely out of place in the timeline we had spent decades building. That was the first crack. It would not be the last. To understand why the image was so unsettling, you need to know what astronomers were expecting to find. The standard model of cosmology, built carefully over the past century, describes the early universe as a place of quiet beginnings. Shortly after the Big Bang, matter was spread nearly uniformly across space. Gravity pulled that matter together gradually. Tiny clumps gathered into larger ones. Over hundreds of millions, then billions of years, galaxies accumulated mass through mergers, grew their spiral arms, and developed the intricate structures we observe today. The early universe was supposed to be a construction site, not a finished city. Webb changed that picture in an afternoon. The telescope itself is an extraordinary instrument. It sits roughly 1 million miles from Earth, 4 times farther than the Moon, orbiting a gravitationally stable point in space known as the second Lagrange point. Its golden mirror stretches nearly 21 feet across, roughly the width of a tennis court. It captures infrared light, the kind emitted by ancient objects, whose shorter wavelengths have been stretched by the expansion of space over billions of years of travel. When that light finally reaches the mirror, it has been journeying for more than 13 billion years. It is the closest thing we have to a time machine built from gold and mathematics. The first images should have contained quiet, dim, embryonic structures. The early universe, according to standard predictions, should have looked like a neighborhood of half-assembled buildings. Instead, Webb showed a skyline. Within weeks of the first deep field release, papers began appearing. A team of astronomers examining 6 specific galaxies, objects observed by researchers at Swinburne University of Technology in Australia, found something that stopped conversation in conference rooms around the world. These 6 galaxies, sitting at distances corresponding to only 500 to 700 million years after the Big Bang, appeared to weigh more than 10 billion times the mass of our Sun. Some looked even larger than the Milky Way, our own galaxy, which required roughly 13 billion years to reach its current size. Mike Boylan-Colchin, an associate professor of astronomy at the University of Texas at Austin, described the discovery with careful words. He said that if the mass estimates were correct, we were in uncharted territory. From a practicing scientist, that phrase carries the same weight as a distress flare fired into the night sky. The deeper problem was not just the mass, it was the rate. To reach those stellar densities in the time available, these galaxies would have needed to convert nearly all of their available hydrogen gas directly into stars, achieving something close to 100% efficiency. Normal galaxies, including our own Milky Way, manage perhaps 5 to 10%. Most of the gas in an ordinary galaxy floats around, dispersed by stellar winds and magnetic fields, never becoming a star at all. The early Webb galaxies behaved as though none of that inefficiency applied. Imagine a bakery that transforms every grain of flour, every drop of water, every trace of yeast into perfect bread with nothing wasted, operating at 10 times normal speed. That is roughly the scale of stellar production these objects implied. Researchers at Johns Hopkins University, led by Nashwan Sabti, pushed back against the most dramatic interpretations. They argued that fitting the standard model to these galaxies broke other predictions, ones that had matched older Hubble Space Telescope data with remarkable precision. Their conclusion was cautious. The problem might not lie in the foundations of cosmology, but in our understanding of how stars and galaxies behave in extreme environments. The debate remains active. Some defend the framework, others see the cracks widening, and while astronomers argued about masses and formation rates, a quieter discovery was accumulating in the same Webb data. A pattern not in brightness, not in mass, but in motion. Galaxies spin. That has been understood for roughly a century. Spiral galaxies, the pinwheel structures that populate the cosmos in such abundance, rotate around their central cores. Some spin clockwise relative to our line of sight, others spin counterclockwise. In a universe where physics operates without preferred directions, you would expect the count to be roughly even. half one way, half the other, like flipping a coin across millions of trials and watching the results settle toward 50-50. That is not what Webb showed. Lior Shamir, an associate professor of computer science at Kansas State University, decided to test the distribution. He pulled images from the JWST Advanced Deep Extragalactic Survey, known by the shortened name JADES. This survey stares at the same patch of sky for extended periods, collecting light from objects so distant and faint that no previous telescope could capture them in comparable detail. Webb's sensitivity and resolution made the resulting images the sharpest ever obtained for objects at those distances. Shamir applied a quantitative method to the spiral galaxies clear enough to analyze. He measured the curl of their arms, the orientation of their disks, the direction of their rotation. 263 galaxies passed the quality threshold, each one a small glowing pinwheel from the early universe. The result was stark. Roughly 2/3 of the galaxies rotated clockwise relative to our point of view. Only about 1/3 rotated counterclockwise. The odds of seeing that kind of imbalance in a genuinely random sample are small. Shamir noted that the asymmetry is so obvious in the images that anyone examining them can see the preference without specialized training or calculation. You do not need statistical tools. You need eyes. The natural first reaction to such a result is suspicion. Maybe the survey covered too small a region of sky. Maybe the field happened to be oriented in a way that favored one direction. Maybe the process used to classify spiral directions had a hidden bias built in. Each of these possibilities was checked. The JADES field sits near the galactic pole, the direction perpendicular to the disk of the Milky Way. This is an advantageous position because it provides a clean line of sight away from the dust and crowding of our home galaxy. The asymmetry held up across multiple measurement methods. It also appeared in earlier Hubble ultra-deep field data, though with smaller numbers and lower statistical significance. Webb simply confirmed the trend with a larger and cleaner sample. The published paper appeared in the monthly notices of the Royal Astronomical Society in March of 2025. The title was simple. The implications were anything but. Either galaxies in the early universe really do prefer one rotational direction, or our entire system for measuring distances and motions in deep space contains a hidden flaw. Both options are dangerous. One rewrites cosmology. The other rewrites every distance measurement we have made in the past 50 years. The number to sit with is 2/3. Out of 263 galaxies examined, roughly 175 rotated clockwise from our viewing angle. Roughly 88 rotated the other way. This is not a borderline statistical artifact. It is a visible lean. In physics, this kind of imbalance receives a specific label. A preferred axis. The phrase sounds clinical. Its meaning is enormous. A preferred axis means the universe has a direction. Not a random scatter of motions, not an even distribution of spin, but a built-in tilt. Something woven into the structure of space from its earliest moments, carried through the formation of hundreds of billions of galaxies, surviving across 13 billion years of cosmic evolution. This idea cuts directly against one of the deepest assumptions in modern physics. The cosmos is supposed to look the same in every direction. That assumption is called isotropy. Combine isotropy with homogeneity, the idea that matter is distributed evenly on the largest scales, and you get the cosmological principle, the foundation on which the math of general relativity, the predictions of the Big Bang, and the structure of the cosmic microwave background all rest. Webb's spinning galaxies are poking a hole in that foundation. There are other hints of directional preferences already present in the data. The cosmic microwave background, the faint thermal glow left over from the first 380,000 years after the Big Bang, contains unusual alignments of hot and cold patches that some researchers have nicknamed the axis of evil. Large-scale flows of galaxy clusters, sometimes described as dark flow, also appear to point in particular directions. Each result carries its own controversy. Each one alone can be dismissed as noise. Stack them together and a pattern starts to emerge. The spinning galaxy result is the cleanest of the group. You do not need complex mathematics to see it. If the asymmetry is real, the question becomes, where did this preferred direction come from? One possibility is straightforward enough to be boring. The motion of our own Milky Way through space causes the Doppler effect, which slightly alters the apparent brightness of distant galaxies depending on which direction they are spinning relative to our motion. If our galaxy's motion happens to favor one configuration over the other, we might detect a false asymmetry driven entirely by our own movement. Shamir acknowledged this possibility in his paper. He noted that if the Doppler explanation is correct, then our standard method for measuring distances to deep universe objects would need to be recalibrated. That recalibration could potentially explain both the Hubble tension and the anomalously massive early galaxies simultaneously. The other explanation is not boring at all. It says the universe was born spinning. The idea sounds like a philosophical error. The universe is everything. There is no outside. There is no fixed background to spin against. How can everything rotate? But the mathematics allows it. General relativity, the framework Einstein completed in 1915, can describe a rotating universe. As far back as the 1940s, the Austrian mathematician Kurt Gödel showed that Einstein's equations possess solutions in which the entire cosmos turns slowly around a global axis. Light traveling along certain paths in such a universe would follow unusual trajectories. In extreme cases, the flow of time itself could form closed loops, theoretically permitting paths that return to their own past. Gödel found this possibility disturbing enough to consider it evidence that the equations required some additional constraint. Most physicists treated the rotating universe as a mathematical curiosity. The Big Bang model with its uniform expansion in all directions won the debate, and spin became a footnote. Then Webb arrived, and the spinning galaxies showed up. If the universe genuinely has a preferred axis, the cleanest physical explanation is that the universe itself was rotating from the start. That rotation would have imprinted a directional preference on the early distribution of matter. Galaxies forming from that matter would inherit a statistical lean. Not absolute, because gravity and chaos can overwhelm small biases, but detectable as a consistent excess in one direction. 2/3 clockwise, 1/3 counterclockwise fits exactly this picture. A rotating universe demands a reference frame, something outside our cosmos for the rotation to be measured against. In ordinary physics, that requirement is nearly impossible to satisfy. The universe is by definition all of space and time. There is no external observer with a compass and a stopwatch, unless our universe is not the only one. Some physicists argue that a rotating universe makes sense if our cosmos is one structure inside a larger one. One bubble in a foam of bubbles. One room in a much bigger building. In that case, the rotation would be measured against the larger frame, and the preferred axis would be inherited from whatever external structure gave birth to our cosmos. The most specific version of this idea is called black hole cosmology, and it is where the strangeness sharpens considerably. Black hole cosmology proposes that our entire observable universe sits inside the interior of a black hole existing in some larger parent universe. The idea is sometimes associated with the name of theoretical physicist Lee Smolin, who explored it in the 1990s, and more recently championed in detailed mathematical form by Nikodem Popławski of the University of New Haven. Imagine a black hole from the outside. It appears as a dark sphere surrounded by a glowing disk of infalling matter. The boundary of the black hole is called the event horizon. Cross it and you cannot return. From the outside, nothing escapes. From the inside, however, the geometry behaves unusually. Space and time exchange roles. The center of the black hole is not a location in space. It is a future moment in time, as unavoidable as the next second of your life. In standard general relativity, matter falling into a black hole converges toward a singularity of infinite density. But Popławski works with a modified version of general relativity called Einstein-Cartan theory. The modification is technical but consequential. Standard general relativity treats space-time as smooth and curvable. Einstein-Cartan theory adds a property called torsion, a kind of twisting of space that arises when matter possesses angular momentum. In ordinary conditions, torsion is negligible. You will never notice it on Earth. Inside a black hole, however, where matter is compressed to extreme densities, the twisting becomes powerful. According to Popławski's calculations, torsion creates a repulsive force at very high densities, strong enough to halt the collapse before it reaches a singularity. Instead of a point of infinite density, the infalling matter bounces, rebounds, and a new region of space opens in a direction that the parent universe cannot access. From inside that new region, the bounce looks like a Big Bang, The expansion of the new space looks like cosmic inflation. The event horizon of the parent black hole forms the outer boundary of what observers inside would call their observable universe. If our universe formed this way, several of its strangest features begin to make sense. The flatness of space, a puzzle that has occupied cosmologists for decades, fits naturally. Matter falling into a black hole arrives with a specific geometric orientation. The expansion that follows would be uniform on large scales. The arrow of time, the fact that the past feels genuinely different from the future, also acquires a source. Material crossing the event horizon of the parent black hole can only move inward. That one-way motion creates a built-in direction, and time inside the new universe inherits it, and the rotation of the parent black hole would imprint a preferred axis on the daughter universe, the same axis that Webb's spinning galaxies appear to remember. Popławski, when asked about the JWST result, said he would be extremely excited if the findings held up. He suggested the simplest explanation for a rotating universe is that it formed inside a rotating black hole. His language was careful. He pointed at a prediction his framework had made and noted the match with the observation. He did not claim victory, but the match was there. Most working cosmologists are not convinced. The idea has elegant features, but very few testable predictions. It is also philosophically uncomfortable. It places our entire cosmos inside another cosmos and raises the obvious next question. What is the parent universe inside of? Some versions of the theory accept an infinite chain. Black holes in our universe spawn new universes. Those new universes spawn more black holes. Each cosmos is a node in an endless tree. The standard Big Bang is also hard to picture. A point of infinite density expanding into existence is not an everyday image. We accept it because the math works, and the predictions match observation. Black hole cosmology is asking for the same patience. Different math, same demand. Show us the predictions. Match them to the data. For now, every black hole visible in a Webb image carries an additional layer of meaning. It is not merely a gravitational monster. Under one theoretical framework, it is a possible birthplace. A door swinging quietly into a universe that will never know its parent. While astronomers debated rotating universes and cosmic handedness, a separate crack was widening in the standard model. This one had nothing to do with spin. It was a crack in something more fundamental: the rate at which the universe is expanding. Edwin Hubble made one of the great discoveries of the 20th century. In 1929, he demonstrated that distant galaxies are moving away from us, and the farther away they are, the faster they recede. The cosmos was not static, it was expanding. The universe had a history, a direction, and a beginning. The rate of that expansion received a name: the Hubble constant. It tells you how fast space itself is stretching as a function of distance. Measure it accurately, and you can calculate the age of the universe, the fate of cosmic structure, and the future evolution of everything. For decades, scientists chased that number. Better telescopes, more precise methods, more distant calibration objects. By the early 2000s, the value appeared to converge around 70 kilometers per second per megaparsec, a unit of cosmic distance equal to about 3.25 light years. Then, a problem emerged. Two different methods of measuring the Hubble constant kept returning two different numbers. The first method uses the cosmic microwave background, the faint thermal glow left by the hot early universe approximately 380,000 years after the Big Bang. Measurements of the microwave background by the Planck satellite, combined with the standard cosmological model, yield a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second method uses a class of pulsating stars called Cepheid variables. These stars brighten and dim on regular cycles. The cycle length reveals the star's true luminosity. Comparing true luminosity to apparent brightness gives a precise distance. Using Cepheids and other calibration objects to measure the distances to far-off galaxies, and then calculating how fast those galaxies are receding, yields a value of approximately 73 kilometers per second per megaparsec. The two numbers should match. They do not. The gap is approximately 9%. In everyday terms, 9% sounds small. In cosmology, it is a chasm deep enough to swallow theories. A gap of that size means the standard model is missing an ingredient, some force, some particle, some phase of the early universe that the equations have not accounted for. The puzzle received a name: the Hubble tension, For more than a decade, researchers attempted to close it. Maybe the Cepheid measurements were contaminated by crowded star fields, nearby stars bleeding their light into the measurements and inflating the apparent brightness. Maybe the microwave background analysis relied on incorrect assumptions about dark matter. Maybe a hidden systematic error was nudging one number up or the other down. Adam Rees, a Nobel laureate from Johns Hopkins University and one of the discoverers of dark energy, led the effort to push Cepheid measurements to ever finer precision. By 2019, his Hubble Space Telescope results had narrowed the uncertainty enough that the disagreement could no longer be attributed to noise or instrument error. The tension was real. Then, Webb launched. With its larger mirror and infrared sensitivity, Webb could pierce through the dust and stellar crowding that had haunted Hubble's measurements. If the Cepheid numbers were wrong, Webb would expose the error. If they were right, the tension would be confirmed beyond any reasonable doubt. Webb pointed at the same galaxies Hubble had studied. It observed the same stars. It applied 3 independent distance measurement methods, including techniques that did not use Cepheids at all. The team assembled the largest sample of Webb data gathered in the telescope's first 2 years of operation. The results arrived in late 2024. The numbers stood. The methods agreed. The error was not on the side of the local measurements. Rees summarized the conclusion clearly. The discrepancy between the observed expansion rate of the universe and the predictions of the standard model suggests that our understanding of the universe may be incomplete. Webb had eliminated the easy escape. The Hubble tension is real. The universe is expanding faster than the equations say it should. To grasp what this means, imagine cosmology as a precise recipe. Take hydrogen, add dark matter, sprinkle in dark energy. Let it expand under gravity for 13.8 billion years. The cake should come out looking like the cosmos we observe. If the recipe is correct, every measurement of the expansion rate should return the same number, regardless of where in cosmic history you look. The early universe and the local universe give different numbers. The local universe is expanding approximately 9% faster than the early universe predicts. That is not within the margin of error. That is a structural failure of the recipe. Some theorists propose a brief burst of additional repulsive energy in the early universe, something that inflated the cosmos slightly faster than standard inflation predicts before fading away. This is sometimes called early dark energy. Add this ingredient, and the early expansion rate adjusts just enough to match local measurements. The problem is that nobody has seen early dark energy. No particle, no field, no clean observational signal. It is a name attached to a blank space in the equation. Other theorists go further. Perhaps the dark energy we already know about is not constant. Recent results from the Dark Energy Spectroscopic Instrument, a survey mapping large swaths of sky, hint that dark energy may be weakening as the universe ages. If true, the future of cosmic expansion becomes uncertain. The acceleration might slow, stall, perhaps eventually reverse. Still others propose that Einstein's equations of gravity require modification at the largest scales. Modified gravity theories appear regularly in the literature. Some survive scrutiny. Most do not. None has yet become the new consensus. A few researchers suggest something subtler. Perhaps the universe has different expansion rates in different regions. We might live inside a large underdense void where things expand slightly faster than the cosmic average. Outside our void, the universe could be expanding more slowly. The tension could be partly a local effect rather than a global one. Webb is helping test several of these scenarios. Its surveys of distant galaxies are mapping the large-scale structure of the cosmos at resolutions no previous instrument could achieve. Each new measurement either tightens the tension or opens a new angle of attack. So far, nothing has resolved it. The crack is wider now, not narrower, and while cosmologists argued about expansion rates, Webb pointed at the deep universe and found something that appeared in nearly every image. Something utterly unexpected. The first sightings looked like noise. Small, faint, reddish specks scattered through the deep field photographs. The initial assumption was that they were ordinary galaxies made redder by dust or by the expansion of space. Background detail, interesting but unremarkable. The kind of faint smudge you log and move past. Then someone noticed how many there were and how strange they were. These objects were given a nickname, little red dots. Astronomers tend towards simple names. The dots are tiny, spanning only a few hundred light years at most. Compare that to the Milky Way, which extends roughly 100,000 light years from edge to edge. A little red dot is to our galaxy what a marble is to a stadium. They glow with deep red colors, suggesting either heavy dust obscuration or extreme cosmological distances, or both. And they appear everywhere in Webb's deep field surveys. 3 to 4 out of every 100 galaxies in some early universe samples resembles one of these objects. That frequency is not a rare anomaly. That is a population. They show up approximately 600 million years after the Big Bang. They reach peak numbers around 800 million years. By 1.5 billion years after the Big Bang, the population thins sharply. By 2 billion years, they have essentially vanished. Whatever these objects are, they had a beginning, a reign, and an end. A short geological era of the cosmos that no previous telescope had the sensitivity to see. The first interpretation was that the dots were active galactic nuclei, tiny galaxies hosting actively growing supermassive black holes, with the black holes feeding, releasing enormous amounts of radiation. The brightness, despite the small size, would fit this explanation. But the standard signatures of active galactic nuclei were missing. No strong X-ray emission, no significant variability over time, no flat infrared spectrum in the expected range. The dots resembled quasars in some respects, and pure starlight in others. The categories were blurring. Then Dale Kochevsky and colleagues found high-velocity gas surrounding several of the dots. Velocities between 2,000 and 4,000 kilometers per second. That kind of motion is uncommon in ordinary galaxies. It is characteristic of gas being whipped by the gravitational influence of an enormous central object. The interpretation shifted again. Perhaps the dots really were powered by black holes, compact, heavily obscured, surrounded by enough material to muffle their X-rays and hide them from the instruments that should have found them. The abundance of the dots became the next puzzle. If each of them contained a supermassive black hole, the early universe must have produced an extraordinary population of these objects in a very short time, far more than standard models anticipated. Some researchers connected this to the broader puzzle of the impossibly massive early galaxies. Both pointed toward a generation of black holes that had grown faster than conventional physics allowed. A team led by Fabio Pacucci at Harvard proposed one mechanism. The dots could form naturally inside dark matter halos with unusually low rotation. Slowly spinning halos would allow gas to fall straight inward without being spun out to the edges first, creating dense, compact, infrared bright sources. The math aligned reasonably well with what Webb was seeing. Other researchers went further. They proposed that the dots might be the visible signatures of a population of primordial black holes, objects that formed not from the deaths of stars, but from the violent quantum conditions of the early universe itself. One of the strangest features of the little red dots is not how they appear, it is how they disappear. Between 600 million and 1.5 billion years after the Big Bang, they are everywhere, field after field, survey after survey. Then, over a span of a few 100 million years, the population collapses. The simplest interpretation is that they evolved into something else. The surrounding gas was eventually expelled by the energy of the growing central black hole. The dust cleared. The compact object grew and transformed into something more recognizable. A galaxy with an active center, a quasar in a host galaxy. The dots did not vanish. They graduated. A theory called the black hole star offers a more striking version of this picture. Under this framework, the dots are not galaxies in the ordinary sense. They are enormous dense clouds of gas with a growing supermassive black hole buried at the center. The cloud absorbs the X-rays that would otherwise identify the central black hole, which explains why most dots are X-ray silent. The cloud glows in infrared under the energy of the black hole within. Imagine a star the size of a galaxy, with a black hole as its heart. That is the image the theory proposes. If it is correct, the dots represent a brief transitional phase in cosmic history, a window in time when supermassive black holes were being assembled inside dense gaseous envelopes before those envelopes dispersed and revealed the monsters inside. The dots disappeared, not because they died, but because they transformed. The surrounding cloud blew off, and what remained was a familiar galaxy with an active core. Webb caught this phase because Webb could see in infrared at sensitivities no previous telescope matched. If the theory holds, the little red dots are the closest thing astronomers have ever obtained to a baby picture of a supermassive black hole. Their formation has puzzled scientists for decades. Webb may have just opened the maternity ward. One of the strongest observational links between the dots and supermassive black hole activity came from an unexpected source. NASA's Chandra X-ray Observatory, which has been monitoring high-energy sources in the cosmos since 1999, had a long catalogue of X-ray detections from before Webb existed. When astronomers began cross-referencing little red dot positions with the Chandra archive, most dots showed no match. They remained stubbornly X-ray quiet, consistent with the black hole star model of heavy obscuration. But one match appeared. A source in the extended Groth strip, a heavily studied region of sky, sat at the exact position of a little red dot identified by Webb. The X-ray signature resembled the kind of emission expected from a quasar. The result was reported in late 2025 and remains one of the strongest direct links between the dots and active supermassive black hole feeding. The interpretation is that the X-ray signal from this particular dot is leaking through a thin spot in the surrounding gas envelope, while most other dots remain too heavily wrapped to reveal their inner fires. Like a fire wrapped in a thick blanket, you feel the warmth. You cannot see the flame. As more Chandra observations are coordinated with Webb's little red dot catalogue, more such leaks may be detected. Each detection would provide direct evidence of a hidden black hole and help separate the genuine black hole stars from other possible explanations. The discovery of the little red dots as a population is itself remarkable. They were not predicted by any standard model before Webb's launch. They appear in nearly every deep field image the telescope has returned. They challenge standard galaxy formation theory. They may rewrite the story of how the first supermassive black holes came to exist. And they are not the only mysterious bright population Webb has found. A team at the University of Missouri, led by astronomy professor Haojing Yan, approached the problem from a different angle. They asked a deliberately narrow question. How many objects in Webb's infrared surveys of the deep universe are brighter than the standard model predicts they should be? They expected a manageable number, perhaps a handful of outliers that would dissolve under closer examination. They found 300 objects scattered across Webb's fields, glowing harder in the infrared than the equations allowed for their estimated positions in cosmic time. 300 candidate early galaxies, sitting in places where they should be faint or absent, blazing with a brightness that the textbook recipe cannot produce. Yan was deliberate with his language. He called them candidates. He noted that even if only a small fraction proved genuine, the discovery could challenge current ideas about early galaxy formation. In cosmology, a challenge that requires only a few confirmed exceptions can be enough to break a model. The recipe is either correct or it is not. The brightness of these objects matters for a reason that connects back to all the other anomalies. Bright early galaxies require either extraordinarily efficient star formation or additional light sources beyond stars. Either option breaks part of the standard picture, either rewriting the rules of stellar formation in extreme environments, or requiring the early universe to have possessed ingredients that the standard accounting has missed. The 300 candidates share certain traits. They are compact, they are red, they exceed the infrared brightness predictions of older models. Some of them may be little red dots. Others may belong to a different population entirely. Confirming their nature will take years of spectroscopic follow-up, careful argument, and the elimination of alternative explanations one by one. Some will prove to be foreground objects coincidentally aligned with the early universe. Others will turn out to be active galactic nuclei mimicking early galaxies. A fraction will likely survive every test, even if only 1 in 10 holds up. That is 30 confirmed objects added to the growing catalogue of things in the early cosmos that the standard model cannot explain. The pattern matters more than any single entry in the catalogue. Webb keeps finding too many bright things too early. Different surveys, different research teams, different measurement techniques, all converging on the same kind of result. A phrase that has begun to circulate quietly in cosmological discussions captures the situation: excess light. The early universe appears to have produced more light in more places than the standard recipe allows. Whether the source of that excess is unusually efficient star formation, primordial black holes contributing additional energy, dark matter interactions releasing radiation, or some unknown process that the equations have not yet encountered, the data keeps pointing at something missing. That phrase has become a recurring theme across multiple open problems. The Hubble tension requires a missing ingredient. The early bright galaxies require a missing ingredient. The little red dots require a missing ingredient. The rotation asymmetry may require one too. A reasonable scientist confronted with 4 separate open puzzles asks whether they all share the same missing ingredient or whether each requires its own. Both possibilities are uncomfortable. A single hidden ingredient that resolves everything simultaneously would be among the most profound discoveries in the history of physics. Multiple separate missing ingredients, each tucked behind a different mystery, would suggest that our current understanding has not merely missed a detail, it has missed several. The recipe was supposed to be simple. It is starting to look like a recipe with several unlabeled jars on the shelf. There is a final dimension to the early galaxy problem that reaches beyond ingredients and tension and rotation. Some of the galaxies appear to be older than the universe itself. The statement sounds like a logical impossibility. The universe is approximately 13.8 billion years old. Nothing inside it can predate its own container. The math is straightforward. Yet several Webb observations have produced stellar age estimates for individual galaxies that press uncomfortably against, and in some cases appear to exceed, the cosmic age limit. The estimates come from analyzing the chemical composition and stellar populations of distant galaxies. Old stars produce specific spectral fingerprints. Heavy elements require time to form, since they are built through cycles of stellar birth, nuclear burning, explosive death, and the dispersal of processed material into new generations of stars. By measuring the metal content and the age distribution of stars in a distant galaxy, astronomers can estimate how long that galaxy has been forming stars. In some Webb images, that estimate exceeds the time available since the Big Bang. The conclusion is not that those galaxies are literally older than the universe. That would violate causality and basic logic. The conclusion is that something in the measurement chain is broken. Either the distance estimate is incorrect, or the age determination method contains an error, or the standard timeline of cosmic expansion is wrong. This discomfort has created an opening for more radical proposals. One of them comes from Rajendra Gupta, a researcher whose work has attracted significant attention by arguing that the universe may be far older than the standard estimate. In a series of detailed papers, Gupta proposes that the cosmos is approximately 26 to 27 billion years old, nearly twice the figure derived from standard cosmology. To arrive at this number, he combines 2 ideas. The first is called covariant coupling constants, the fundamental constants of nature, the strength of gravity, the speed of light. The charge of an electron may shift very slightly across cosmic time in coordinated ways that preserve certain measured relationships while allowing the underlying numbers to evolve. The second is an older idea called tired light, which proposes that photons gradually lose energy as they travel through space, shifting toward the red end of the spectrum without, requiring the expansion of space as the cause-tired light was proposed in the 1920s by the Swiss astronomer Fritz Zwicky as an alternative to Hubble's expanding universe. It was examined carefully and largely rejected over the following decades. The cosmic microwave background, the fade rate of distant supernovae, the time dilation observed in supernova light curves, all of these behave in ways that match cosmic expansion and not a static universe with tired photons. By the 1970s, the Big Bang model had won the debate. Tired light became a footnote. But the mature early galaxies have reopened the conversation. Gupta argues that combining a modified tired light contribution with covarying physical constants produces a coherent, cosmological framework that matches Webb's observations without the standard model's embarrassment over early galaxy masses. The galaxies look mature because they are mature. The universe gave them more time to build. If the standard age of 13.8 billion years is wrong, and the true age is closer to 27 billion years, a great deal changes. The timeline of structure formation relaxes. The mature early galaxies become ordinary. They had plenty of time to assemble their stars. Their masses are not anomalies. Their chemical compositions are not impossible. They are simply old galaxies. The mainstream response has been skeptical. The standard age is not a loose parameter. It is tightly constrained by multiple independent measurements. The cosmic microwave background power spectrum, the abundances of light elements produced in the first few minutes after the Big Bang, the clustering of galaxies on large scales, all of these converge on the same cosmic age within the framework of the standard model. Changing the age by a factor of 2 requires explaining why all of these diverse measurements consistently return a younger figure. Critics argue that Gupta's framework cannot simultaneously satisfy all the existing constraints. Some observations that tired light struggles to match, particularly the observed time dilation in supernova light curves, remain problematic for his framework even in its modernized form. The debate is ongoing in technical literature. Most working cosmologists remain skeptical, but the conversation now happens in real conference rooms rather than on the margins of fringe publications. What changed? Webb's data. The mature early galaxies created enough discomfort with the standard model that ideas previously dismissed without much consideration are receiving fresh evaluations. If standard physics cannot accommodate the observations comfortably, alternative frameworks get a hearing. The honest assessment is that mainstream cosmology has not embraced tired light or covariant constants as serious contenders. Most researchers see the discomfort as evidence that the standard model requires modification, not that it requires replacement. But the conversation about replacement, which would have been considered unserious 5 years ago, is now happening in legitimate scientific venues. Nothing about the current state of cosmology suggests the field is about to collapse. The standard model has accumulated too much predictive success to be abandoned over a collection of anomalies, however persistent. What is happening is something more gradual and more interesting. The model is being stress-tested at scales and resolutions it was never designed to face. What began as a measurement problem, a telescope returning unexpected images, has grown into something more structural. The anomalies are diverse. They appear in data from different instruments, different research groups, different methodologies. They have been checked and cross-checked. They persist. Each anomaly in isolation can be handled. The early bright galaxies, maybe unusual star formation efficiency, the rotation asymmetry, possibly a Doppler artifact from our own galactic motion, the Hubble tension, perhaps an undetected systematic in one of the measurement chains, the little red dots, a new class of active galactic nucleus not anticipated by previous models. But explaining all of them independently requires a series of separate coincidences, each plausible on its own, all happening at once. Scientists call this kind of situation a proliferation of epicycles, a reference to the increasingly complex adjustments that medieval astronomers made to preserve the Earth-centered model of the solar system before Copernicus, replaced it with something cleaner, the possibility that one underlying change to the standard framework explains all the anomalies simultaneously is more elegant and more alarming than any individual fix. What could that underlying change be? One possibility centers on dark matter. The standard model assumes dark matter consists of massive, slow-moving particles that cluster gravitationally into dense halos. A team led by Alvaro Pozo at the Donostia International Physics Center, working with collaborators from Arizona State University, MIT, and Harvard, examined the shapes of young galaxies in Webb images and found something the standard picture struggles to explain. Many of the earliest galaxies appear strikingly elongated, not spherical, not disc-shaped, but stretched, prolate, resembling cigars or American footballs rather than spheres or flat discs. The team ran simulations testing 3 dark matter models: cold dark matter as the standard scenario, warm dark matter in which the particles move faster and suppress clustering on small scales, and wave dark matter in which the particles are so extraordinarily light that they exhibit quantum wave behavior on cosmological scales. Cold dark matter. Simulations failed to produce elongated early galaxies in significant numbers. The cosmic web produced by cold dark matter is clumpy, full of small, dense knots, and galaxies forming inside those knots tend toward roundness. Warm dark matter simulations succeeded. So did wave dark matter simulations. Both of these alternatives produce smoother, more filamentary cosmic webs, with gas flowing along long, narrow channels and naturally assembling into elongated structures. The implication is that dark matter may not be the slow, heavy particle the standard model assumes. It might be something lighter, something wave-like, something with quantum behavior on galactic scales. Rogelio Windhorst, a Regent Professor at Arizona State University and an interdisciplinary scientist for Webb, described the observation. He noted that standard expanding universe models expect galaxies to grow from small clumps of dark matter that assemble through gravity. But Webb suggests that the earliest galaxies may be embedded in marked filamentary structures more consistent with an ultralight, quantum dark matter particle. This dark matter candidate sometimes called fuzzy dark matter or wave dark matter, has been proposed theoretically for years. The particles would have masses many orders of magnitude smaller than standard candidates. Their quantum wavelengths would be so enormous that on the scale of a dwarf galaxy, the dark matter would behave not like a collection of point particles, but like a continuous field, oscillating gently across light years of space. Observational advantages of this model are not limited to galaxy shapes. Wave dark matter produces smooth cores at the centers of galaxies rather than the dense cusps that cold dark matter predicts. Observations of dwarf galaxies in our local cosmic neighborhoods sometimes show exactly those smooth cores. The discrepancy between cold dark matter predictions and observed galaxy core profiles has been known for years. Wave dark matter naturally resolves it. The detection challenge is severe. Ultralight particles do not bounce off atoms. They do not produce visible radiation. They interact almost exclusively through gravity. The main experimental avenue has been to search for their wave-like gravitational effects on precision instruments, atomic clocks, and gravitational wave detectors. So far, no confirmed detection has occurred. Webb has now provided indirect evidence from a completely different direction. The shapes of early galaxies in the deep universe are more consistent with a smoother, filamentary dark matter distribution than with the clumpy, clustered distribution that cold dark matter produces. That evidence will not by itself overturn decades of successful cold dark matter predictions, but it adds a specific and clear data point to the case for alternatives. If wave dark matter eventually proves to be correct, the consequences reach deep into both cosmology and particle physics. The weakly interacting massive particle, the leading dark matter candidate for which underground experiments have been searching for 3 decades, would be discarded. Direct detection experiments tuned to heavy particle interactions would become historical artifacts. New searches focused on wave-like signatures and precision gravitational measurements would become the priority. The matter content of the universe, the way structure formed, the behavior of galaxy halos, all of it would require revision. The change would not eliminate the Big Bang. It would not overthrow general relativity, but it would rewrite a substantial section of the physical story between those pillars. The early history of black holes is equally unsettled. The conventional account says that black holes form from dying stars. A massive star exhausts its nuclear fuel. Its core collapses under gravity, and depending on the initial mass, the collapse ends in either a neutron star or a black hole. Repeat this process across hundreds of millions of years of stellar evolution, and you accumulate the population of stellar mass black holes observed throughout galaxies today. Supermassive black holes, the ones that anchor the centers of almost every large galaxy, including our own, are more complex. They weigh millions to billions of times the mass of our Sun. Stars cannot produce them directly. The standard picture involves smaller seed black holes that grow over cosmic time by feeding on surrounding gas and by merging with each other. The process should require a very long time. Webb has shown supermassive black holes existing at times when this process should not have been complete. Galaxies only a few 100 million years after the Big Bang already host black holes weighing millions of solar masses. The standard story does not have time to build them. The escape route the data points toward is called primordial black holes, a concept with a history extending back to the 1960s and 70s. Yakov Zeldovich and Stephen Hawking both contributed to the original proposal. The idea is that the early universe was not perfectly uniform. Tiny variations in energy density existed everywhere. If a particular region happened to be sufficiently overdense, gravitational collapse could occur directly, without waiting for stars to form. The result would be a black hole produced in the first seconds or minutes after the Big Bang. The range of possible masses for primordial black holes spans an enormous spectrum. The smallest ones, with masses comparable to everyday objects, would have evaporated long ago through the quantum process Hawking described. Larger ones could persist to the present day, invisible among ordinary matter but gravitationally influential. The largest, possibly weighing thousands or even millions of solar masses, would be exactly the seeds that the early Webb galaxies seemed to require. For decades, primordial black holes remained a theoretical curiosity. The standard picture of stellar collapse seemed sufficient to account for known black holes, and invoking primordial ones added complexity without clear observational. Support.Webb changed the calculation. A paper by Zijian, Shen and colleagues at the Hong Kong University of Science and Technology used a statistical framework to examine whether primordial black holes could explain the early supermassive black holes seen in Webb's images. Their preferred model involved a distribution of primordial seeds with masses concentrated around 750 times the mass of our Sun. Drop these seeds into dense gas clouds inside dark matter halos, allow them to feed at extraordinary rates for brief periods, permit them to merge with each other over a few 100 million years, and the result matches what Webb observes. The math fits. The framework provides a simultaneous explanation for both the early supermassive black holes and the unusually massive early galaxies that host them. Earlier theoretical work by Alexander Dolgoff, a physicist at Novosibirsk State University, anticipated aspects of this picture. In the early 1990s, Dolgoff and Joseph Silk published a paper proposing that primordial black holes could form with a specific mass distribution called log normal. This was a technical prediction made before any telescope could test it, and before the instruments needed to test it had even been designed. The prediction lay quietly in the literature for 3 decades. When Webb returned its first images of the early universe and teams of astronomers began working backward to understand what kinds of seeds could have produced what the telescope was seeing, Dolgoff's 30-year-old distribution appeared again. The log-normal mass function he and Silk had proposed in the early 90s aligned with the masses needed to seed early supermassive black holes. A specific prediction made before the data existed turned out to match the eventual observation. That kind of alignment does not prove a theory, but it raises the probability significantly. It is the gold standard of theoretical cosmology. Predict, then verify. Dolgoff himself has noted the match in more recent publications, arguing that the primordial black hole framework predicted the observed population of early developed galaxies and quasars. Whether the full match between theory and observation holds up under continued scrutiny is being evaluated by research groups around the world. If primordial black holes are eventually confirmed as the seeds of early galaxies, the implications extend beyond explaining the Webb anomalies. The formation of these objects in the first second after the Big Bang would reveal something profound about the conditions of that era. The energies, the quantum fluctuations, the symmetry-breaking processes that shaped the earliest universe. The primordial black holes themselves would serve as fossils, carrying encoded information about an epoch that no other observational tool can probe. Some versions of the primordial black hole scenario also offer a candidate for dark matter. If these objects exist in sufficient numbers with the right mass distribution, they could account for the invisible scaffolding that holds galaxies together without requiring any exotic new particle. 2 mysteries with one answer. A paper by researchers including Yukun Yifan and others examined whether primordial black holes could simultaneously explain early galaxy formation and serve as dark matter. Their conclusion was that certain mass ranges work for both purposes simultaneously, while others fail. The question remains open. The constraints are active areas of research. What is clear is that primordial black holes have moved from a fringe idea to a mainstream consideration over the past 3 years. The Webb observations provided a platform that decades of theoretical work could not. The objects are no longer merely a theoretical possibility. They are one of the leading candidates for explaining several of the telescope's most persistent surprises. For the scientific enterprise as a whole, this moment has a specific texture. It does not feel like crisis. A crisis would involve evidence directly contradicting a well-tested core principle, demanding immediate replacement of a central framework. What cosmology is experiencing is more like a series of careful, accumulating questions. The mature early galaxies ask, how did structure form so fast? The rotation asymmetry asks, does the universe have a preferred direction? The Hubble tension asks, what is the universe missing that allows it to expand differently than predicted? The little red dots ask, what were the first supermassive black holes, and how did they grow? The elongated young galaxies ask, what is dark matter really made of? None of these questions has yet forced the abandonment of the standard model. Each of them, however, requires an answer that the standard model cannot currently provide without modification. The most senior researchers in the field have noticed the pattern. The cosmologist asked about the state of the discipline described it as a renaissance rather than a crisis. A renaissance implies intense rebuilding, the recognition that old certainties are incomplete. and the expansion of what is considered possible. That description fits the current moment well. General relativity is more than 110 years old. Einstein published the theory in 1915. In the decades since, it has passed every experimental test thrown at it. The bending of starlight by the sun's gravity, the orbital decay of binary pulsars, the detection of gravitational waves from colliding black holes, the precise behavior of GPS satellites that would drift out of sync without relativistic corrections. Each test confirmed the theory to extraordinary accuracy, yet general relativity also predicts its own limits. At the centers of black holes, the equations produce singularities, points of infinite density where the mathematics breaks down. At the moment of the Big Bang, the equations break down again. These are not flaws in the theory. They are signposts pointing to deeper physics that the theory itself cannot describe. Quantum mechanics, the other great pillar of modern physics, has a similar relationship with its boundaries. Its predictions match experiment with extraordinary precision. But quantum mechanics and general relativity have never been fully unified. At the smallest scales, where quantum effects should dominate even gravitational settings, the two theories produce incompatible results. The search for a theory of quantum gravity has occupied generations of theorists. String theory and loop quantum gravity are the leading candidates for a unified description. Neither has yet produced clear experimental predictions. Both make claims about scales far smaller than current instruments can directly probe. Webb does not test quantum gravity directly, but its observations of the early universe push against the regime where quantum gravitational effects should matter. The early universe conditions, traced backward from what Webb sees, approach the boundary where general relativity and quantum mechanics must somehow be reconciled. The anomalies Webb has detected may be the first observational hints of where that reconciliation changes physics in observable ways. The mature early galaxies, the rotation asymmetry, the early supermassive black holes all depend on conditions in the very early cosmos. Slight modifications to either general relativity or quantum mechanics in those extreme conditions could produce different outcomes downstream. The Webb observations might be probing the edge of where current frameworks apply. Some theorists are already exploring modified gravity scenarios that affect early universe cosmology. Others are examining quantum effects on cosmological scales. Each proposal makes specific predictions about what Webb should observe. The comparison is being made. So far, no single modified theory has emerged as the clear winner. The standard combination of general relativity plus the standard model of particle physics and cosmology continues to provide the best overall fit to the totality of observations, including the Webb data. What the Webb data has done is open doors to alternative frameworks that were previously kept closed by the absence of distinguishing observations. The pattern of how physics has evolved is well documented. Newton's mechanics described everyday motion with extraordinary accuracy. It was extended rather than replaced by Einstein at high speeds and strong gravity. Einstein's gravity might in turn require extension, not replacement, by some future framework that handles cosmic boundaries more naturally. Webb may be helping identify where those extensions need to be applied. The view from where we currently stand is both humbling and exhilarating. The framework that has guided our understanding of the cosmos for a century is encountering observations at its boundaries. The boundary is not yet a wall, but it is clearly there, and the observations that press against it are accumulating with each new Webb survey. Consider briefly what the cosmos looks like if all the most radical interpretations of current data turn out to be correct. Not because they necessarily will, but because sketching the extreme case reveals how much the current data has expanded the space of serious possibilities. The universe was born inside a rotating black hole existing in a parent cosmos. Its initial rotation imprinted a directional preference on the matter that would later form galaxies, producing the 2/3 clockwise asymmetry that Webb observed. Primordial black holes formed in the first second after the Big Bang, seeding both the dark matter distribution and the first massive galaxies. Dark matter consists of ultralight wave-like particles rather than heavy point particles, producing the smooth filamentary cosmic web that explains the elongated shapes of early galaxies. The Hubble tension reflects a genuine physical effect, perhaps evolving dark energy or a modification to early universe physics, that the standard model has not yet incorporated. This is not the cosmos described in any current textbook. It is, however, a cosmos that current data permits as a serious possibility. The fact that such a picture can be constructed from legitimate scientific observations and defended in peer-reviewed journals represents a major expansion of the boundaries of what is considered scientifically plausible. 20 years ago, most of these ideas occupied the fringes of cosmology, defended by small groups of dedicated theorists and dismissed by the majority. Webb has moved the edges closer to the center. The mainstream has expanded to include possibilities it would have ruled out a decade earlier. This matters for a reason that goes beyond the specific scientific content. The way physics advances is not by conservative extension of existing frameworks alone. It advances when observations force frameworks beyond their comfortable range of application and demand something new. The new thing is usually built on the foundation of the old, but it adds structure, corrects errors, and reaches to scales the old framework could not address. Newton's physics was not wrong. It was incomplete. Einstein's extensions revealed that incompleteness and produced new predictions that Newton's framework could not have generated. If the current standard model of cosmology is similarly incomplete, the observations that reveal that incompleteness are the most valuable scientific data the field can possess. Webb is producing that data at a rate no previous telescope could match. The anomalies are real. They are cross-checked. They persist under scrutiny. They are converging on something that the standard model in its current form cannot cleanly accommodate. Whether the eventual resolution involves adding missing ingredients to the existing framework or replacing its foundations with something structurally different is the central question of contemporary cosmology. The answer will not arrive in a single paper or a single year. The data will continue to accumulate. Theoretical proposals will be tested and evaluated. Some will survive. Most will not. The eventual winner will likely be recognized as obvious in retrospect, as fundamental advances usually are. For now, the cosmos that Webb is revealing is a place more complicated, more interconnected, and more strange than standard cosmology had predicted. The simplest version of the cosmic story is not quite right. The galaxies in the early universe were too massive, too soon. The cosmic expansion is moving faster locally than the early universe predicts. The first supermassive black holes appeared before the standard recipe had time to build them. 2/3 of the visible spiral galaxies in the deep universe are spinning in the same direction. A population of compact red objects blazed through the first 2 billion years of cosmic history and then disappeared without clear explanation. The shapes of early galaxies matched the predictions of a quantum wave-like dark matter more than the predictions of the standard heavy particle version. Each of these findings, alone, could be absorbed by careful modification of existing theories. Together, they are asking for something more than modifications. They are asking for a rethinking. The James Webb Space Telescope was designed to observe the earliest structures in the universe and to test the predictions of standard cosmology in the regime where they had never been directly verified. It has done exactly that. The test results were not what was anticipated. The telescope showed us a cosmos that keeps its own counsel. The standard story fits most of the evidence well. The parts that do not fit are growing in number and clarity. What fits and what does not are no longer the same categories they were at launch. The universe is bigger than the map we drew of it. The map is being revised. It will take the efforts of many more researchers, many more telescopes, and many more years of careful argument to produce a map that fits the territory. What Webb has ensured is that the territory is now visible. The galaxies are sharp, the anomalies are documented, and the questions are precise. Precise questions, aimed at the right observations, have a way of finding answers. Whether the answers involve a universe born inside a rotating black hole, a cosmos filled with primordial black holes that seeded both dark matter and the first galaxies, dark matter made of waves rather than particles, or something that none of the current proposals anticipates, the process of finding those answers has genuinely begun. The cosmos has been patient for billions of years. It has kept its deepest secrets through every previous generation of observers, through every telescope we pointed at the sky before Webb arrived. It is finally beginning to share them. If what Webb is showing us has captured your attention, consider staying close to this conversation. The next set of images will be even more revealing. The next generation of surveys is already underway, and somewhere in the data flowing back from that golden mirror, 1 million miles from Earth, the next answer is already waiting to be found. The story of how Webb arrived at this moment is itself worth understanding. The telescope was conceived in the 1990s as the successor to the Hubble Space Telescope. Its design went through decades of revision. The mirror grew larger, the infrared sensitivity was refined, the engineering challenges multiplied. At one point, cost overruns and technical setbacks led to serious discussions about cancellation. The telescope finally launched in December of 2021 aboard an Ariane 5 rocket from the Guyana Space Center in French Guiana. The launch was unusually precise. The trajectory was so accurate that the telescope used only a fraction of the fuel reserves originally allocated for course corrections. That fuel savings translates directly into extended operational life. Webb is now expected to function for significantly more than its originally planned 10-year mission. The journey to the telescope's observation point took approximately 1 month. During that time, the telescope went through a complex unfolding sequence. The sun shield, roughly the size of a tennis court and consisting of 5 ultra-thin layers of material, opened layer by layer. The mirror segments, 18 hexagonal pieces of beryllium coated in a thin layer of gold chosen for its excellent infrared reflectivity, unfolded and locked into position. The secondary mirror, suspended on a tripod of booms extending in front of the primary, deployed. Each step had to work correctly the first time. There was no way to send astronauts to fix a problem. The telescope sits too far from Earth for any crewed vehicle currently in existence. All of it worked. By July of 2022, NASA released the first full science images. The response was immediate and worldwide. Astronomers who had spent careers preparing for the telescope's launch found themselves staring at pictures that immediately challenged the models they had built to interpret what the telescope would show. The preparation had been extensive. Before launch, teams of theorists had run simulations of what the early universe should look like when observed in Webb's wavelength range with Webb's resolution. They published predictions. They produced catalogs of what to expect. They developed tools for analyzing the images. All of that preparation was sensible and scientifically sound. What it could not do was anticipate being wrong. The early universe, as it actually appears in Webb's images, is brighter than the simulations predicted, more structured than the models expected, and populated by objects that the theoretical frameworks had not imagined. The gap between prediction and observation is not a signal of incompetent preparation. It is a signal of genuine discovery. No amount of preparation can simulate a universe that behaves differently from the equations used to describe it.
The calibration of scientific expectations against reality is one of the most important functions that telescopes serve. Webb has performed this function with exceptional clarity. The telescope has several science instruments working in different parts of the infrared spectrum. The near-infrared camera, known as NIRCam, captures the deep field images that most prominently display the early galaxy populations. The near-infrared spectrograph, NIRSpec, can simultaneously take spectra of up to 200 objects, splitting their light into wavelength components that reveal chemical composition, temperature, velocity, and distance. The mid-infrared instrument, MIRI, captures longer wavelength infrared light, revealing cooler dust emission and objects that are invisible to shorter wavelength detectors. Together, these instruments allow astronomers not just to see the early universe but to measure it. Spectra determine distances precisely, resolving ambiguities that photometry alone cannot settle. They reveal what elements are present and in what abundances. They measure the velocities of gas clouds, revealing whether black holes are blowing material out of galaxies or pulling it in. They detect the signature of molecular hydrogen in the youngest star-forming regions. The spectroscopic capabilities of Webb have been as important as its imaging in revealing the anomalies described throughout this discussion. The little red dots were initially identified in images. Their unusual properties were confirmed through spectra. The velocity of gas around several of them, measured spectroscopically, was what pointed toward black hole activity rather than ordinary stellar populations. The Hubble tension result from Webb came specifically from precise spectroscopic measurements of Cepheid variable stars, cross-validated against other standard candles using the telescope's sharper resolution. The rotation asymmetry in galaxy spins came from photometric analysis of deep imaging, the kind that Webb's near-infrared camera produces with unprecedented clarity. Each instrument is contributing to the picture. The picture that has emerged is more complicated than anyone planned for, more interesting than the models suggested, and more demanding of explanation than the field has faced in a generation. There is an aspect of this situation that scientific papers rarely address, but that practicing researchers discuss. Science advances most rapidly when observations surprise the people who design the experiments. Expected results confirm existing frameworks. Unexpected results create new problems, and new problems create new physics. The Hubble Space Telescope, Webb's predecessor, provided extraordinary data for 3 decades and confirmed many predictions of standard cosmology. It also revealed that the expansion of the universe was accelerating, a completely unanticipated result that earned its discoverers the Nobel Prize in Physics in 2011. That discovery required the introduction of dark energy into the standard model. Dark energy, which now accounts for approximately 68% of the total energy content of the universe, was entirely absent from the model before the Hubble data demanded it. Webb is in a similar position. The telescope is revealing things that are not in the current model. Whether those things will require additions to the model comparable in scale to the dark energy addition, or whether they will require structural changes to the model itself, is not yet clear. What is clear is that the scientific process is working. Observations are being made, predictions are being tested, failures of prediction are being documented, theoretical explanations are being proposed, tested, refined, and discarded or retained according to how well they match the data. This is not a crisis. This is science functioning at its most productive. The timeline for resolving the current anomalies is not short. Individual puzzles in cosmology have taken decades to resolve. The nature of dark energy has been uncertain since its discovery in 1998. 27 years later, it remains one of the most pressing open questions in physics. The Hubble tension has been building since approximately 2013, and after more than a decade of effort, remains unresolved. The little red dots, the rotation asymmetry, the early bright galaxies, the elongated young galaxy shapes, the early supermassive black holes, all of these are recent discoveries. The observational data for them is still being accumulated. The theoretical frameworks for explaining them are still being developed. The competition between rival explanations has barely begun in most cases. A decade from now, the landscape will look different. Some of the current anomalies will likely have been resolved by better data or improved theoretical understanding. Others will probably persist and deepen. New anomalies will almost certainly have appeared that have not been anticipated from the current vantage point. The history of astronomy strongly suggests that better telescopes do not simplify the cosmos. They reveal more of its complexity. The Roman Space Telescope, scheduled for launch in the mid-2020s, will survey large regions of sky with a sensitivity comparable to Webb's. Its wide field of view, substantially larger than Webb's, will allow statistical studies of galaxy populations at the scales needed to decisively test whether the rotation asymmetry is real across the full sky or whether it is limited to specific regions. The same surveys will provide enormous samples for studying early galaxy shapes, testing dark matter models, and measuring the Hubble constant through yet additional independent methods. Ground-based facilities currently under construction will add their own capabilities. The extremely large telescope, being built in the Chilean Atacama Desert, will have a primary mirror 39 meters across, larger than anything currently operating. Its spectroscopic instruments will be able to take detailed spectra of individual stars in nearby galaxies that are currently too faint for such measurements. That capability will allow direct tests of stellar population ages in ways that could help resolve the question of galaxies appearing older than the universe. The next generation of gravitational wave detectors, including the planned space-based LISA mission, will observe black hole mergers at cosmological distances. If primordial black holes exist in the expected mass range, the gravitational wave signatures of their mergers should be detectable. A confirmed detection would provide direct evidence for primordial black holes as a population. Each of these instruments will add pieces to the puzzle. The puzzle has become visible because Webb removed the observational barrier that was hiding it. The telescope was designed to see what no previous instrument could see. It achieved that goal. In achieving it, it has revealed that what lies beyond the previous limits of observation is not a smooth continuation of the known cosmos, but a more complicated structure with features that do not match the current map. The researchers working on these questions are not discouraged by the complications. They are energized by them. The questions that have emerged from Webb's first years of operation are genuine scientific questions with answers that matter. The answers will reveal something true about the physical universe. Whatever that something is, it will be more accurate than what is currently understood, and it will be the foundation for the next generation of questions. That is what progress looks like. Not the smooth confirmation of existing models, not the quiet extension of known physics to slightly larger scales, but the confrontation with a universe that turns out to be stranger and richer than the framework built to describe it. The framework gets rebuilt. The new framework handles the strangeness. The process repeats. The universe has been here for approximately 14 billion years by current estimates, possibly longer if some of the more radical proposals prove correct. It has been indifferent to our attempts to understand it for all of that time. The last few years, since Webb first opened its golden eye, are the most recent chapter in a very long effort to see clearly. The seeing is getting better, the picture is getting more complex, the science is getting more interesting. Stand at the edge of the observable universe for a moment, at least conceptually. In that direction, at the farthest distances Webb can resolve, lie the galaxies that started this conversation. Too massive, too soon, spinning in a direction they should not prefer, glowing with red light from objects that should not exist, expanding away from us at a rate that does not match what the early universe predicts. Each of those galaxies is sending us a message. The message has been traveling for more than 13 billion years. Webb is reading it for the first time. The message says, "The map you have is incomplete." The map makers are at work. The universe is patient. The answers will come. There is something worth dwelling on about the specific character of the anomalies Webb has uncovered. They are not the kind of surprises that emerge from instrument malfunction or measurement error. They are the kind that emerge when observations are made with exceptional precision in a regime where previous measurements were imprecise or absent entirely. The early universe, the first billion years after the Big Bang, was previously accessible only in outline. Hubble could see it, but the images were blurry and the objects it could resolve were the brightest and most exceptional. The statistical properties of early galaxy populations were poorly constrained. The shapes of early galaxies were essentially unknowable at the resolutions available. The chemical compositions of stars in those galaxies could not be determined. The masses of early supermassive black holes were estimated from limited samples, with large uncertainties. Webb changed each of these constraints simultaneously. Better resolution, better sensitivity, better spectroscopic capability, broader wavelength coverage. The telescope did not reveal a different universe. It revealed the same universe in sharper focus. And in sharper focus, features appeared that were not visible in the blur. This is a pattern familiar from the history of science. The microscope revealed that biological tissues were composed of cells, a fact invisible to the naked eye but profoundly important for understanding life. The spectrograph revealed that the sun is composed primarily of hydrogen and helium, a fact invisible to visible light photography but fundamental to stellar physics. Radio telescopes revealed that ordinary stars are embedded in a cosmos filled with pulsars, quasars, and cosmic microwave background radiation, none of which had been detected before the appropriate instruments existed. Each time a new kind of seeing becomes available, the universe displays features that were always there but previously inaccessible. The features revealed by Webb are the features of the early universe at cosmological resolution. They were always there. Now they are visible. The scientific response is to ask what the features mean. The answer requires understanding why those features exist, which means tracing their origins back to the physics of the early universe. That physics, it is becoming clear, is not fully described by the Standard Model in its current form. This should not be surprising. The Standard Model of cosmology was developed primarily to describe the universe as observed from the present era and to extrapolate backward to the very early universe through mathematical extension. The early universe conditions were never directly accessible before Webb. Extending a theory to describe conditions, it was never tested against, and finding that the extension requires modification is not a failure of the theory. It is the normal outcome of genuine scientific progress. Newton's law of gravitation was developed to describe the motions of objects under everyday gravitational conditions. When it was extended to describe the orbit of Mercury, the most precise planetary orbit measurement available in the early 20th century, it failed by a small but definitive amount. That failure was not a sign that Newton was wrong about apples falling from trees. It was a sign that gravity at its most extreme required a more complete description. Einstein provided that description. The Standard Model of cosmology is extraordinarily successful at describing the universe from approximately 1 second after the Big Bang onward, at scales from galaxy clusters down to stellar populations. Webb is observing conditions at earlier times and in environments more extreme than those that were available for testing when the model was developed. Finding that the model requires modification in those regimes is exactly what the history of physics leads us to expect. The specific nature of the required modification is where the current debate is focused. Every group of researchers has a different candidate. Some favor extending the dark matter description. Others favor modifying the early universe energy content. Some are looking at modifications to gravity at cosmological scales. Others are exploring the possibility that the initial conditions of the Big Bang itself were different from what the simplest inflationary models predict. Inflation, the theory that the universe underwent an extraordinarily rapid exponential expansion in the first tiny fractions of a second after the Big Bang, is a cornerstone of modern cosmology. Inflation explains why the universe is so flat, why the cosmic microwave background is so uniform across regions of sky that should never have been in causal contact, and why the initial density fluctuations that seeded structure formation have the specific statistical character that is observed. But inflation is also a theory with many variants. The energy scale at which inflation occurred, the specific mechanism that drove it and then ended it, the precise character of the density fluctuations it produced, all of these depend on the particular inflationary model chosen. Different models make different predictions for the early universe. Webb is testing those predictions at a level of detail that was never previously possible. The mature early galaxies, the little red dots, the early supermassive black holes all constrain the character of the density fluctuations that inflation produced and how those fluctuations subsequently evolved. Some inflationary models are more consistent with the Webb observations than others. The comparison between models and data is an active area of work. If inflation needs modification, that modification would affect predictions for the cosmic microwave background at levels that future microwave background experiments might be able to detect. The connection between what Webb sees in galaxy populations and what microwave background telescopes might see in the radiation from the early universe is a productive research direction. The CMB-S4 project, a planned network of ground-based microwave background detectors, is designed to measure the polarization of the cosmic microwave background with unprecedented precision. That polarization carries information about the gravitational wave background produced during inflation. If Webb's observations constrain inflationary models in specific ways, CMB-S4 will be testing those same constraints from a completely different observational direction. Consistency or inconsistency between the two datasets will be highly informative. This is how modern cosmology works, not through single decisive observations, but through a web of interconnected measurements that collectively constrain the space of viable theories. Webb is one node in that web, a particularly important node because it addresses the early universe directly, but still one node among many. The question of what happens next in this scientific story depends on which of the current anomalies prove real and which turn out to be measurement artifacts, how quickly the theoretical community converges on explanations, and what the next generation of instruments reveals. The rotation asymmetry in galaxy spins will be tested by surveys of thousands of additional fields with different telescope orientations and using multiple methods for determining spin direction. If the effect is real and not a measurement artifact, it will appear consistently across all of these tests. If it disappears under closer examination, the result will be revised or withdrawn. That is how science works, and it is entirely healthy. The Hubble tension will be tested by independent measurement methods currently being developed. New ways of measuring distances to distant galaxies, not dependent on the Cepheid distance ladder, are being validated and deployed. If the tension is real, all methods will return a local expansion rate higher than the early universe prediction. If a systematic error is hiding somewhere in the current measurements, new methods may find and correct it. The early bright galaxies and little red dots will accumulate more spectroscopic data as Webb continues operations and as follow-up observations are scheduled. Each confirmed spectrum either validates or challenges the current interpretation. The statistical picture will clarify over time. The primordial black hole hypothesis will be tested in part by gravitational wave observations. If primordial black holes exist with masses in the relevant range, their merger signatures should appear in gravitational wave detector data as the sensitivity of those detectors improves. The third generation of ground-based gravitational wave detectors, Einstein Telescope and Cosmic Explorer, are designed with the sensitivity needed to detect mergers at cosmological distances. Their data, combined with Webb's observations of early galaxy populations, would provide a powerful test. The dark matter properties will be constrained by comparisons of simulated galaxy populations with observed ones. If warm or wave dark matter produces a better match to Webb's early galaxy shapes and sizes than cold dark matter, that evidence will accumulate across multiple surveys and simulation comparisons. Definitive resolution will require very large statistical samples and careful handling of the uncertainties in galaxy formation physics. Each of these tests is underway. The results will not all arrive simultaneously. The picture will become clearer gradually through the accumulation of data and the progressive elimination of alternatives. The universe does not reveal itself all at once. It reveals itself piece by piece, observation by observation, in response to the quality of the questions being asked and the precision of the instruments available to answer them. Webb has raised the quality of the questions. It has revealed that the early universe contains features the standard model did not predict. It has given the theoretical community specific, well-characterized anomalies to explain. Those anomalies, whether they ultimately require modifications to the standard model or its replacement by something fundamentally different, are the most productive inputs that observational astronomy can provide to theoretical physics. The universe we live in has been here for billions of years. It has seen the formation of the first stars and galaxies, the assembly of galaxy clusters, the evolution of the cosmic web, the birth of stars that were old when the sun formed, and the explosion of those stars scattering heavy elements into space, where they eventually condensed into planets and living things. We are made from material that was processed through multiple generations of stars before ending up in the solar system. The iron in human blood was forged in the cores of massive stars that exploded billions of years before the sun existed. The carbon in organic molecules was produced in stellar interiors and scattered by stellar winds. The hydrogen in water is as old as the universe itself. We are, in the most literal sense, part of the story that Webb is reading. The atoms in our bodies were in the early universe when the first anomalous galaxies Webb has detected were forming. Those atoms have been through processes that the standard model describes imperfectly, and that the anomalies Webb has found suggest we do not yet fully understand. Understanding the early universe better is not an abstract intellectual exercise. It is an attempt to understand the origins of everything that exists, including the conditions that made the emergence of complex matter possible. The physics of the early universe set the initial conditions for everything that followed. Galaxy formation, star formation, planetary formation, chemistry, biology, consciousness. All of it traces back to those initial conditions. The standard model describes those initial conditions well enough to predict a universe compatible with our existence. The Webb anomalies suggest that the description is incomplete. The complete description, when it eventually emerges, will account for the early bright galaxies, the rotating cosmos, the primordial black holes, the wave-like dark matter, and whatever other features are still waiting to be discovered. That complete description will be a more accurate account of why the universe is what it is, and why we are possible within it. The work is ongoing. The telescope is still watching. Every 90 minutes or so, it completes another circuit of its observing program and returns more light from the early universe to the detectors. The data is processed, archived, and made available to researchers around the world who are asking questions that would have been unanswerable 3 years ago. The cosmos has kept its secrets for billions of years. It takes the right instrument, the right question, and the right moment in the history of science to begin unlocking them. Webb is that instrument. The questions are the right ones. The moment is now. The deepest question that the Webb anomalies raise is not about galaxies or dark matter or expansion rates. It is about the framework of physics itself and how that framework relates to the observable universe. Modern physics rests on two pillars that have both proven extraordinarily successful and that remain incompatible with each other at the theoretical level. General relativity describes the large-scale structure of spacetime, the behavior of gravity, and the dynamics of the universe on cosmic scales. Quantum mechanics describes the behavior of matter and energy at the smallest scales, the interactions of particles, and the probabilistic character of measurement. Both theories are accurate to a remarkable degree within their respective domains. General relativity correctly predicts the expansion of the universe, the bending of light by gravity, the existence of black holes, and the existence of gravitational waves. Quantum mechanics correctly predicts the behavior of atoms, the properties of semiconductors, the existence of antimatter, and the precise energy levels of electrons in any element. The problem is that the two frameworks are built on incompatible foundations. General relativity describes a smooth, continuous spacetime that curves in response to matter and energy. Quantum mechanics describes a world of discrete values, probabilistic outcomes, and fundamental uncertainty. When you try to describe gravity using the quantum mechanical framework, the equations produce infinities that cannot be renormalized away. When you try to incorporate quantum mechanics into the fabric of spacetime, the smooth, continuous background that general relativity assumes becomes incompatible with the discrete, probabilistic nature of quantum fields. This incompatibility does not matter in most practical situations. Quantum effects are important at very small scales. Gravitational effects become strong only at very large masses or very high densities. For most of the universe, most of the time, the two theories can be applied independently without conflict. But there are regimes where both matter simultaneously. The centers of black holes, the moment of the Big Bang, the conditions of the early universe a fraction of a second after the Big Bang, when densities were high enough that quantum effects were important even for gravity. These are precisely the regimes that the Webb anomalies are probing, at least indirectly. The early bright galaxies, the primordial black holes, the conditions that set the initial rotation of the universe, all of these trace back to the first moments after the Big Bang, when the physics of quantum gravity was relevant. The standard model of cosmology describes those early moments using a combination of general relativity and quantum field theory that works in practice, but is known to be incomplete in principle. If the early universe conditions were slightly different from what the standard model assumes at the level of quantum gravity, the consequences would propagate forward through cosmic time and show up eventually in the statistical properties of galaxy populations. Webb is measuring those statistical properties with unprecedented precision. This means that the Webb anomalies might ultimately point toward a resolution of the incompatibility between general relativity and quantum mechanics. Not directly, not obviously, but through the chain of consequences that connects early universe physics to the properties of the galaxy populations that Webb observes. String theory, one of the leading candidates for a theory of quantum gravity, makes specific predictions about the number and types of particles in nature, and about the character of spacetime at the smallest scales. Those predictions have proven difficult to test experimentally, because the relevant scales are far smaller than any current accelerator can probe. But string theory also makes predictions about the early universe cosmology, about the character of inflation, about the spectrum of density fluctuations that inflation produces. If string theory-inspired modifications to early universe cosmology produce predictions that match the Webb anomalies better than the standard model, that would constitute an indirect test of the theory at energy scales corresponding to the early universe, scales far above what particle accelerators can reach. This is one of the reasons that cosmological observations have become increasingly important as tests of fundamental physics theories. Loop quantum gravity. The other major candidate for quantum gravity unification makes different predictions. In loop quantum gravity, spacetime is not continuous but consists of discrete quantum units of space, something like a fabric woven from elementary loops rather than a smooth continuum. At the Planck scale, the smallest meaningful distance in physics, this discreteness becomes important. In the early universe, when the entire observable cosmos was compressed into a region smaller than an atomic nucleus, the discreteness of spacetime under loop quantum gravity would have profound effects. Poplawski's Einstein-Cartan theory, which provides the physical mechanism for the black hole cosmology scenario, is related to loop quantum gravity through the concept of torsion. Both theories incorporate the idea that the fabric of spacetime has additional structure beyond the simple curvature that standard general relativity describes. In loop quantum gravity, that additional structure is discreteness. In Einstein-Cartan theory, it is torsion. The physical consequences of these additional structures, particularly in extreme conditions like those inside black holes or at the Big Bang, are the subject of active research. If the universe was indeed born inside a rotating black hole, and if the torsion mechanism provides a bounce rather than a singularity, then the initial conditions of our universe are set by the physical conditions of a black hole in a parent universe. Those conditions would include a specific rotation rate, a specific energy density, and a specific pattern of quantum fluctuations that would serve as the seeds of structure formation. The character of those initial conditions would be imprinted on everything that formed afterward, including the statistical distribution of galaxy rotation, directions that Webb has now measured. The chain of reasoning from a Webb observation of galaxy spin Directions to a conclusion about the nature of quantum gravity is long and contains many uncertain links. But the chain exists. Theoretical cosmology has a history of connecting observations at large scales to physics at small scales through exactly such chains of reasoning. The discovery that the expansion of the universe is accelerating, from Hubble Space Telescope observations of distant supernovae, pointed toward the existence of dark energy, which in turn connected to fundamental questions in quantum field theory about the energy of empty space. The vacuum energy problem, which asks why the quantum mechanical energy of empty space is so much smaller than particle physics calculations predict, remains one of the deepest unsolved problems in physics. Cosmological observations drove us to that problem. The Webb anomalies may be driving us toward a different set of fundamental questions. Why is the early universe brighter than predicted? Why does it have a preferred rotation direction? Why did supermassive black holes form so quickly? Why do the shapes of early galaxies suggest a smoother dark matter distribution than cold dark matter predicts? Each of these questions has answers that connect to fundamental physics. The connection may not be immediately obvious, but it is there. The history of physics gives good reason to expect that following the chains of reasoning from these observational questions to their physical origins will reveal something genuinely new. Not just new parameters within existing frameworks, but new physical concepts that the frameworks in their current form cannot accommodate. The introduction of quantum mechanics in the early 20th century was not merely a modification of classical physics. It required an entirely new conceptual framework, built on superposition, probability amplitudes, and measurement disturbance, that was incompatible with classical intuitions, but accurately described the behavior of matter at small scales. The introduction of general relativity similarly required new concepts: curved spacetime, the equivalence of mass and energy, the relativity of simultaneity, that were incompatible with Newtonian intuitions, but more accurately described the behavior of matter at high speeds and strong gravity. If the Webb anomalies are pointing toward a new framework, that framework will require new concepts. What those concepts are is not yet known. The theoretical tools for identifying them are being developed now, in response to the specific character of the anomalies that Webb has revealed. Science at its most productive operates in exactly this way: observations that do not fit, theories that strain to accommodate them, new theoretical frameworks that explain the failures and predict new features, observations that test those new frameworks. Each cycle advances the understanding. We are at the beginning of a new cycle. Webb has provided the anomalies that started. The theoretical work is underway. The tests are being designed. The observations needed to perform those tests are being gathered. The cycle will take time to complete. That is not a reason for impatience. It is a reason for the specific kind of attention that rewards patience. The next decade in cosmology will be one of the most productive in the history of the science. The data being collected now will be analyzed for years. The theoretical frameworks being developed now will be tested against measurements that do not yet exist. The instruments being designed and built now will reveal features of the cosmos that cannot currently be anticipated. The universe is large, the questions are hard, the answers are worth finding. What Webb has done in its first years of operation is transform cosmology from a science with a settled narrative and a few open questions at the edges into a science with a settled framework and a growing catalog of anomalies that press against its foundations. That is not a setback. It is progress. The settled narrative was not wrong, but it was incomplete. The incompleteness is now visible in specific and quantifiable ways. An incomplete map with identified gaps is far more useful than a complete map of a smaller territory. The gaps tell you where to explore next. They tell you what questions to ask and what instruments to build. They give direction to scientific effort in a way that confirmatory results cannot. The gaps Webb has opened are large enough to be scientifically significant and small enough that they do not destroy the existing framework. They point toward specific modifications or extensions rather than wholesale replacement. That is the most productive kind of scientific situation. Not crisis, but productive tension. Not collapse, but refinement under pressure. The researchers working on these questions understand this. The ones who seem most energized by the Webb results are not those who believe the standard model has failed. They are the ones who recognize that the anomalies are real, that they point toward something missing, and that the something missing is within reach of determination with the tools and instruments now available. That is the spirit in which good science is done, not triumphalism about proven theories, not nihilism about overturned models, but genuine engagement with observations that do not yet fit and genuine effort to understand why they do not fit and what understanding why will reveal. The Webb telescope continues to watch. The archive continues to grow. The papers continue to be written and debated and refined. The universe continues to be more complicated, more interesting, and more honest than any single model has yet managed to describe. Whatever comes next, the era of knowing the cosmos well enough to be surprised by it is upon us. Webb made it happen. The surprises are here. The work of understanding them has just begun. There is a specific kind of intellectual experience that the best science communication tries to convey. It is the experience of standing at the edge of the known and looking outward into what is not yet understood, while holding in mind everything that has been established and recognizing that both the established knowledge and the open frontier are equally real and equally important. The established knowledge in cosmology is substantial. The Big Bang framework has been tested across an enormous range of observations and emerged consistently. The cosmic microwave background measurements by Planck and other satellites have constrained the parameters of the standard model to percent-level precision. The large-scale structure of the universe, the cosmic web of filaments and voids and galaxy clusters, matches the predictions of cold, dark matter cosmology with remarkable accuracy across a range of scales. None of this is in dispute. The Webb anomalies are not evidence that the Big Bang did not happen, or that dark matter does not exist, or that the universe is not approximately 14 billion years old. They are evidence that the detailed physics of the early universe is more complex than the simplest standard model predicts. The rough outlines of the cosmic story are secure. The details are being revised. This distinction matters because science communication often fails to convey it. Anomalies get reported as paradigm-destroying crises. The nuance that separates the standard model needs modification from the standard model is wrong gets lost. The result is a public perception that scientists are constantly overturning everything, that nothing is known, that one anomalous result can undermine decades of established knowledge. That is not how science works. Established knowledge is not overturned by single observations. It is adjusted, extended, and refined through the accumulation of evidence that collectively points toward specific modifications. The standard model of cosmology will not be abandoned because of the Webb anomalies. It will be improved by the response to them. What will be abandoned, eventually, is whatever specific assumption within the standard model turns out to be most inconsistent with the full body of Webb observations. That assumption will be replaced by something more accurate. The more accurate something will make better predictions. Those predictions will be tested. The model will continue to evolve. This is the scientific process in action. It is slower than dramatic narratives suggest and more reliable than cynical narratives imply. It works because it is self-correcting. Errors persist only until they are checked by new observations. New observations create new questions. New questions motivate new instruments. New instruments provide new observations. Webb is one step in a very long process. a particularly important step because it addressed the regime of the early universe with unprecedented precision, but a step, not an endpoint. The researchers working with Webb data are acutely aware of this. They are producing results as carefully as they can, acknowledging uncertainties honestly, and situating their findings within the larger context of what is established and what remains open. The papers that have attracted the most attention are not reckless claims of paradigm overthrow. They are careful measurements with appropriate error bars and honest discussions of what the results do and do not imply. That carefulness is what makes the scientific enterprise trustworthy. It is also what makes the current anomalies significant. When careful researchers with appropriate methodologies consistently find that early universe observations do not match standard model predictions, and when those findings are reproduced by independent teams using different methods, the scientific community takes them seriously. That is the appropriate response. The anomalies are being taken seriously. The response is substantial. Theoretical papers proposing explanations are appearing at high rates. Observational follow-up programs are being designed and executed. Collaborations between theorists and observers are forming around specific open questions. The scientific literature is alive with debate about what the Webb results mean. That activity is the visible signature of a field engaging productively with unexpected results. The debate will resolve, eventually, through the accumulation of evidence sufficient to distinguish between competing explanations. The resolution will tell us something true about the universe that we do not currently know. What that something is remains to be discovered, but the discovery is underway. The golden mirror is still turning. The infrared photons from the early universe are still arriving. Each one carries information about a time when the cosmos was young and dense, and filled with processes that our equations describe imperfectly. Each one is a message from a universe that is more interesting than any model of it. We are learning to read the messages. The reading takes time. It takes care. It takes the accumulated effort of thousands of researchers working on different aspects of the same problem, from instrument calibration to theoretical modeling, from spectral analysis to statistical comparison with simulations. But it is happening. The cosmos is revealing itself to us at the precision level, where the incomplete parts of our understanding become visible. That is the most important thing Webb has given us. Not specific anomalies, though those matter enormously, but the precision needed to ask the right questions at the right scales. The precision that transforms cosmology from a science where broad features can be confirmed to a science where specific mechanisms can be tested and specific unknowns can be identified. The unknowns are now identified. The mechanisms are being tested. The answers are being sought. The universe, patient as ever, is waiting for us to catch up. Let us close by returning to the images themselves. The pictures Webb returns are not abstractions. They are photographs of real objects at real distances, each one a window into a specific moment in cosmic history. When you look at a Webb deep field image, you are looking at a collection of galaxies at many different distances. The nearest ones appear larger, more detailed, showing spiral arms and dust lanes and bright central regions. As you move to fainter and smaller objects, you are looking at galaxies progressively farther away and therefore progressively earlier in cosmic time. The faintest, smallest, most distant objects in a Webb deep field are galaxies as they existed when the universe was only a few 100 million years old. Light that left them 13 billion years ago is only now reaching the telescope's mirror. When that light departed, the planet Earth did not exist. The sun had not yet formed. The elements of which we are made had not yet been synthesized and scattered by exploding stars. The universe was still in its infancy. And yet the Webb images show that even in that infancy, something recognizable as structure had already formed. Galaxies existed. They were building stars. They were hosting enormous black holes. Some of them were already more massive than our current home galaxy. The structure of the cosmos was not a blank canvas at that point. It was already a painting, albeit an early one, and the painting did not match the sketches that theory had predicted. That mismatch, documented in paper after paper over the first years of Webb operations, is the fundamental scientific surprise that this discussion has been exploring. It is not a mismatch in the broad strokes. The Big Bang happened, the universe expanded, matter formed, stars ignited, galaxies assembled. All of that is confirmed. The mismatch is in the details of how quickly and how efficiently the early stages of that process occurred. The details matter because physics is in the details. The broad strokes are compatible with many different underlying mechanisms. The details constrain which mechanisms are actually at work. Webb has provided the details. They do not match the standard mechanism. This is the most honest and accurate way to describe the scientific situation. Not crisis, not catastrophe, not the collapse of cosmology. A specific and precise mismatch between observation and the detailed predictions of the standard model, in the regime of the early universe, documented by careful researchers using reliable methods, reproduced across independent teams and observational programs. The mismatch points toward something missing, finding that something is the work of the coming years. The work will be done. The universe has been here for billions of years. It will be here for billions more. The missing something has been present since the beginning. It has been waiting to be found. It is waiting still, hidden in the equations and the observations, for the right question to be asked in the right way with the right instruments. Webb has given us better instruments than any previous generation of scientists possessed. The right questions are being formed now, in response to what the instruments have shown. The answers are not yet known. But asking the right questions is the first step. And we are finally, after billions of years of cosmic patience and several decades of human preparation, asking them.